Hello, everyone, and welcome to another class of ATMO 620. Hope you're all doing well. Okay, so the journey into the microphysics of clouds continues. Just a reminder to know, where we're standing. We started off looking at, thermodynamics, and then we talked about how cloud condensation nuclei facilitate the formation of cloud droplets. And then we started talking about the growth of the droplets that form on cloud condensation nuclei. A growth we assumed to be by condensation, which, if you think about it, it kind of makes sense, right? What else could it be? We're considering warm precipitation, so rain. And so, what else could there be? Well, as it turns out, there is something else. Condensation is all fine, and it's certainly a very important process for cloud particles, cloud droplets. But condensation cannot be the only thing that is happening in a cloud. And the reason why we think that is that we derived some equations to predict the growth of the radius of a cloud particle, right? I hope you remember of a cloud droplet. I hope you remember that. Now, using these equations, we can turn these around and we can compute the time it takes for cloud droplets to grow to a certain size. So suppose that you measure some spectrum of raindrop radii at the surface. How long did it took a cloud particle to grow to that radius? If you do the calculation, and we'll talk about this later on today, if you do this calculation, it turns out that it takes much, much longer than what is observed. So something else must be happening within a cloud. So why don't we start today's topic? And today we will introduce today's topic essentially by talking about rain. Rain is important for a variety of reasons. Here in Hawaii, it's important because it constitutes 100% of the precipitation that falls in Hawaii. But even outside of Hawaii, rain constitutes a significant source of precipitation, if you will. Most of rain precipitation falls as rain. Sure, there is snow, and having lived many years in Boston, I know this. But snow isn't the most important. Well, isn't the most frequent form of precipitation, the most abundant form of precipitation. Rain is, okay. And a lot of this rain is produced by clouds that don't have an ice face, meaning that these are clouds that don't grow tall enough to reach a level in the troposphere where liquid droplets freeze or where ice nuclei form. Okay, we'll talk about this in a couple of lectures. These clouds are typically called warm clouds, and the shallow cumulus clouds of Hawaii are an example of these shallow cumulus clouds. Obviously, of these warm clouds. Obviously, there are many more types of clouds than there are many more types of warm clouds than just shallow cumulus clouds. We don't have many here, but stratocumulus clouds, which you can find abundantly off the coasts of Chile, of South America. These are another example of warm clouds. Now, as it turns out, the principal mechanism for the formation of rain in these type of clouds is coalescence, which means as an ESL, when I first saw this term, I had to look it up. It's essentially, if you will, it's collision. Well, it's droplets merging together. Okay. And collisions are one way that droplets can coalesce, but not the only one. Okay. And so coalescence is what explains the fast production of raindrops. Here you can see that rain can be formed in as little as 20 minutes. And you start with cloud droplets with radii of about 10 micrometers with 100 per centimeter cube. And in 20 minutes, you go to droplets with 1 millimeter and 1,000 per meter cube. So it's a lower concentration, but a much, much higher radius, right? So how does that happen? And if you were to compute, as I said, if you were to compute the time it takes for diffusion to condensation to help you grow to that from 10 micrometers to 1 millimeter, that would be much too long. It would be much longer than 20 minutes. Okay, and typically a millimeter of a raindrop of 1 millimeter diameter is the result of hundreds of thousands, if not millions, of collisions. Something similar happens for rain that falls from other types of clouds as well, like cumulonimbus clouds and thunderstorms and whatnot. But even in very simple shallow cumulus clouds, there are so many collisions that produce raindrops. And we will talk about today. We'll start seeing a little bit of. We'll start to see some quantitative analysis of these collisions, right? So how can we quantify the chance that a collision happens, and how does collision help the growth of a radius? When we think about this, we need to think about the very complex setting of a droplet that is falling in the air. This is the falling, right? And there are other droplets. And when these droplets collide, your intuition might suggest that they would merge automatically, because that's what that's what water does. But for very, very small droplets, the surface tension is really, really high. And therefore, when two really small droplets collide with each other, it's not guaranteed that they would merge into something bigger, but they could also bounce off each other. Okay, so the details of collisions between cloud droplets are a little bit more complicated than just saying, well, droplets collide and that's all. We talked about the growth of radii, the growth of a radius of a cloud droplet by condensation. And if you remember, I'm going to write it for the 100th time. We had this equation for rdr dt equal s minus 1 fk plus fd, and we said let's just call this psi. Okay, let's assume, just for simplicity, that this psi remains constant. This is a bit of a stretch, but maybe the cumulus cloud is really, really small, kind of flat, and so conditions don't really change all that much. In that case, this term here, we can also rewrite it as 1/2 dr squared dt of psi. I mean, I don't have to redo this. Hopefully you remembered. And so fast forward, you get to this solution. Okay, so r, the radius, grows as the square root of time, essentially plus some constant term. Okay, and so if we estimate this psi, then we can turn this around and we can determine how long it takes to grow to a certain radius, and that would literally be t or delta t. That would be rt squared minus r0 squared divided by psi. I'm not going to go through all the calculation of psi, but if you want to go from let's say 10 or 20 micrometers in this case, and you want to go to 1 millimeter, okay? Let's say that this delta T you estimated through observations, and let's just use a value of 10 minutes, which is kind of what some observations suggest, or it's a typical value for the initiation. And so we know this. Let's say that supersaturation is about 0.5%, which is, if you remember last class, it's kind of within the range of what we observe, or at least that is the maximum supersaturation. It was in the range of the maximum supersaturation that we observed. We can back off. My English is failing me. Well, we can estimate what conditions you'd need in order to have this growth happen in about 10 minutes with this supersaturation. And it turns out that in order to have that, this kind of supersaturation and this kind of growth, yada, 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 if you only had condensation at play, then you'd need a really, really fast updraft. Okay, and you need 5 meters per second updraft. Now, 5 meters per second is really, really high. And in some thunderstorms, in some severe convective cases, maybe you do have 5 meters per second. But in the warm cumulus clouds that we have here in Hawaii, for example, 5 meters per second is too much. Typical values are of the order of a meter per second. Okay, so they're much smaller than 5 meters per second. So this is unrealistic, and this is what suggests that condensation is not the only thing that is at work in these warm clouds. Also, we observe normally that the spectrum of cloud droplets broadens. Okay, so if you start, let's say that this is the distribution of cloud droplets at time equal 0. After some time, at time equal t, this is a function of radius, right? And this is just to say that this is at time t0. At time t, the spectrum is, typically we observe spectra that are much, much broader with very large droplets. Again, this is really hard to explain using simply condensation, okay? At some point, people thought that maybe giant sea salt nuclei could help in creating some of these large droplets, but there's no evidence of that. At least not when the book was not when the book was written. But generally, no. There's no evidence that giant sea salt nuclei are the main responsible for the broadening of the spectrum, particularly at larger radius. Now, granted, giant sea salt nuclei, and I know that some of you, looking at you, Katie, are thinking about this. Giant sea salt nuclei are important, right? Okay, so don't get me wrong. They are important in forming cloud droplets and forming large drops, but they are not the main, at least the statement here is that they're not the main contributor for larger raindrops, okay? What is believed to be at play here is that mixing actually between the cloud and the environment might help to explain this broadening here. Now, I want to discuss briefly a phenomenon that if you will study clouds in your life and you will think about clouds in your life, it will be sort of an omnipresent companion to you. And this phenomenon that we want to talk about is mixing, or otherwise known as entrainment, okay? Entrainment. And what this is that this is the cloud that is growing. And as the cloud grows, because it's so turbulent, at the interface of this cloud, there naturally are turbulent eddies that ingest some air from the environment and also kick out some air from the cloud. There's also some entrainment here at the top. Entrainment or mixing, they are sort of synonymous, okay? And from below, you have the updraft that is sustaining the growth of the cumulus clouds, okay? Now, one reason why I said that you would think for a very long time you'd think about entrainment in your life is that there's still a lot that we don't know and that we don't understand about entrainment. And there still are different views, different ways to think about entrainment. It's still something that we're trying to quantify, if you will, that we're trying to better understand. When we think about the mixing that happens, let's zoom in the picture that I showed before. Let's say that this is the cloud edge, and this is some cloudy air, and this is some environmental air. And let's say that some environmental air is mixed within the cloud. Okay. In this case, what could happen is that, one way that this could happen is that the mixing occurs really, really quickly, and it occurs. It's kind of mixing happens really quickly and completely. So that if we look at the cloud from above, right, all the cloud is affected by this process. Okay, so mixing is a lot quicker than anything else that could happen in the cloud. This particular kind of mixing is called homogeneous mixing. And in this case, if you think about it, you are introducing drier air pretty much everywhere in the cloud at a given height. So this drier air in particular, it's subsaturated. So this air is at a lower vapor pressure. And so when you mix it inside of the cloud, it's going to lower the vapor pressure. It's going to lower the saturation ratio and the supersaturation within the cloud, potentially causing some of the droplets to evaporate. Okay, so in this case, the dilution of entrained air will reduce all the radius of all the droplets. So if you had your distribution of radii, they would all move by a certain amount. Okay. The underlying assumption here, of course, just to remind you, is that the time that is required for mixing is much, much shorter compared to the time that is required by evaporation, right? And that allowed us to say the mixing is instantaneous and kind of complete, right, across the cloud at a given height. So this does not really help us much, because if you think about it, let's say you have a spectrum of droplets at time t0. Because of entrainment or because of homogeneous mixing, this will move to the right. And so at a later time, it will move a little bit down like this. And so even if it maintained the shape, you'd have more clouds at more droplets at smaller radii. So this could explain why the spectrum broadens towards the smaller radii, but it doesn't really explain why the spectrum also broadens typically towards larger radii as well, because in this case there aren't larger radii. The other view of mixing, on the other hand, is that mixing is inhomogeneous, meaning that in this case, from this perspective, the time that is required for the mixing is a lot bigger than the time that is required by evaporation, right? And so in this case, let's say you're looking at a cloud from above. Okay, so this is X and this is Y. There's a parcel of air, dry air, that goes in. This will come in and it will cause disruption here, and it will cause some droplets to evaporate here, but it will not affect the rest of the cloud. Okay? So the regions that are directly exposed to the mixing will experience evaporation, so sort of a lowering of the supersaturation and potentially an evaporation of the droplets. But the rest of the cloud is not affected. This region here then later will mix with the rest of the cloud, by diffusion. Yeah, by diffusion, droplets from here will start to affect the rest of the cloud, and potentially, because this is, remember, locally drier, it will cause it will cause the saturation to slowly lower in the rest of the cloud, but it will be much slower. So it has been suggested that inhomogeneous mixing could actually help, and particularly when air is entrained at the top of the cloud. It's been suggested that it could help with the production of larger droplets. How does this work? Well, imagine that you have your cloud. Some air is being entrained from the top. Now, this air locally interacts with cloud parcels, and it evaporates some droplets while maintaining saturation. Okay. Now, this air is continuing to descend because it's cold and dry and kind of heavy, and so it continues to descend. And as it descends, the droplets, the smaller droplets that were in these parcels, have evaporated, and what has remained are larger droplets. Okay, and these larger droplets were too big to evaporate completely, and it's going down. Okay, they keep going down until at some point they will reach this mixing with the rest of the cloud will be complete. And now you have these large droplets inside of a cloud, inside of a saturated cloud. And these droplets will start to grow by condensation, and they'll become much, much larger. Okay, particularly when you go towards the lower regions of the cloud where you have supersaturation, or sort of a lot of supersaturation, if you will. Okay, and so this could potentially explain why the spectra tends to broaden towards the larger radii. It may be confusing because we're talking about, if you look at it from this point of view, from that point of view. But again, as I said before, mixing and entrainment in general, it's still a topic on which very little is known, and so, even though the book was written many years ago, and you may be tempted to think that science back then was not as settled and as precise as today. Well, actually, there's still so much that we don't understand, even today. So this is still something that is a bit of an open question, even today. Okay. So this helps us understand why we have larger droplets why the spectrum of the droplets broaden with time, but it still doesn't explain why rain can be formed in such a short time. Why you go from zero to rain in 10 minutes. Well, people researching on this through the years started thinking about the possibility that the collision and coalescence may be factors that mattered in explaining why you may have sort of a faster generation of raindrops. First of all, is it reasonable to think that we have collisions? Well, I would argue that it is because, first of all, clouds are extremely turbulent environments. And so, you have inside of a cloud, even without going to, think about thunderstorms, even like simple shallow cumulus clouds, inside you have a lot of eddies of various sizes, okay? Because this is what turbulence does and kind of looks like, right? And so droplets are moving in all possible crazy directions. We talked about a spectrum, right, of droplets. And so the droplets, even at the beginning, they have different radii. Different radii means different volumes, which ultimately, density of water, liquid water being roughly constant, it means different masses. And so this is something that we talked about last class. If you have an eddy, a turbulent eddy that is moving cloud drops, right, in a certain weird direction, the larger cloud drops have a higher inertia, and therefore, if this eddy, turns and does something crazy, these are more likely to be ejected from the eddy, right? While these ones travel at the same, let's even imagine that they travel at the same speed, some will be able to follow the whole eddy here, but some will be ejected, right? And so if you had almost like a vortex structure, right? Something like this that is growing, right? Some larger droplets will not make the curve, and maybe they may be able to collide. Another thing that happens in the clouds is that when droplets are then large enough, they start to fall. They settle, we say. We call this gravitational settling. So it's nice to know that, when cloud drops are mature, they can settle down. But unfortunately, there's nothing for them to rest on, and so they just fall towards the ground in what we call rain. We don't know that these will actually reach the ground. We don't know that they will not evaporate, whatever. Also, one interesting thing that you might think about is that in thunderstorms, this is my depiction of a thunderstorm. In thunderstorms, you have really, really strong electric fields. And so you might think that electric fields may be enough to pull water particles in different directions. But actually, it turns out that even though electric fields are important for a variety of reasons, i.e. lightnings, they're not particularly important for collision processes. So they do not help generally attract particles together, okay? Also, last thing I wanted to point out, collision does not mean coalescence, okay? Remember, we'll see this later, small droplets have typically really strong surface tensions, and so they bounce off each other. Why do they have really strong surface tensions? Well, because remember that curvature for a sphere in general, curvature goes like 1 over r, where r is the radius, and surface tension is proportional to curvature. And so whenever you have a really, really strong curvature, surface tension is really, really high. And curvature is higher, and therefore surface tension is higher for smaller droplets, okay, than for larger droplets. So, okay, let me drink water. What could happen Excuse me. Excuse me. What could happen when two droplets collide? Again, we think about droplets like as really, really small objects. And so probably we think that their dynamics is very simple, but we couldn't be more wrong about that. The dynamics of droplets and droplet collision is extremely complex and convoluted. So a few things could happen when two droplets collide. Let's say droplet 1 and droplet 2 collide. The first thing that could happen is that they bounce apart. So just like two hard spheres, they bounce apart. The second thing that could happen is that they're joined in sort of a liquid matrimony, and they just become one thing, a larger droplet, okay? That has twice the volume, of course. They could... so this was option number 1. This is option number 2. Option number 3 is that they could actually coalesce for a little bit, and then for whatever reason they break up and they go their separate ways. Okay. There's also an option 4, which is very interesting. It's kind of challenging to predict. That they come together in something, but then they break up, into two droplets that are different from the ones that they started off with. Okay. Why could all these be the case? Well, these two are probably the ones that we would have thought about, that we would have considered as the most probable. This one is kind of slightly counterintuitive, but you have to imagine that these droplets are falling, right? And when they come together, maybe they come together. We can draw it here. Maybe they come together and they're joined only by a few molecules, something like this. And so what is holding these two together maybe is not particularly strong. And so this is going down, okay? And so there's like air that's pushing on this, and so maybe this will be severed and the two will continue to fall down. Possibility. The other option is that they come together, but you have to imagine that even when they come together, their coming together is not a peaceful process whereby they just merge. This is a surface that, even though droplets are small, but this is still sort of a flexible surface. And you could think of this a little bit as the surface of a drum. A drum, the skin of the drum, the thing that you beat on. The point being that because this is so flexible, it can oscillate, it can vibrate, and the collision is certainly going to excite some waves along this surface, and the turbulent air that's falling around the droplet is also going to stimulate some modes, and it could be that one of these modes, or the combination of all these modes, there'll be some kind of interference, constructive interference, destructive interference, whatever. But these modes might conspire and may actually deform the cloud droplet to look like this or something. Twist it a little bit. And this becomes really, really thin. Okay. And so with a similar logic to, option number 3 here, now maybe something happens. Air is pushing against this, and this may be severed. And so you have two different droplets as a result. So always keep in mind that droplets are still, even though they're small, they are kind of, they still are a very complex dynamical system is what I meant to say. Okay. Which one of these options may be realized? Well, it depends on a lot of things. It depends on drop size. It may even depend on electrical forces. Electrical forces are not determinant to, they're not crucial to determine whether there will be a collision or not, but they may play a role in breaking some of these links, some of these bonds, or weakening them, for example. We call coalescence efficiency the ratio of all the coalescences, if that's even a word, to the number of collisions, meaning given a certain number of collisions, what is the fraction that results into permanent coalescence? Well, that is the coalescence efficiency, which is not collision efficiency. Okay, please keep that in mind. Collision efficiency may be just a problem. We'll actually talk about this later, and it's mainly a problem of hard spheres meeting each other. But coalescence efficiency is a lot more complicated because all these different outcomes could result. Okay, first thing that we need when we talk about droplets is understand what happens through their fall. I hope this is not breaking news to anybody, but droplets typically, they accelerate pretty quickly, like everything accelerates that's falling in the universe, and they accelerate pretty quickly, but then they reach a velocity that is kind of constant. Okay, they reach a velocity that remains constant throughout their fall. Okay, this velocity is typically called terminal fall velocity, or terminal fall speed. And this is generally achieved by any object, if you give it enough time to fall, typically develops terminal fall speed. Clearly, if it's a meteorite, it may actually impact on the surface before the terminal fall speed is achieved. But droplets are small enough that this can be achieved with no problem. Why is there a terminal fall speed? Why is that? When does that happen? Well, you have to remember that, and if you watched astronaut movies like Apollo 13 or whatever, I don't know if that's too old a reference for you guys, but air actually is kind of a viscous fluid. It's a hard word for me to pronounce. Viscous fluid that exerts a drag on whatever is moving through it. And so I was mentioning the astronaut references, the astronaut movies, because in every respectable astronaut movie, whenever the spaceship is entering back in the atmosphere, you see like flames around the spaceship and whatnot. And that happens because of this drag force. The drag force is so intense that it actually heats up whatever is falling through it. Okay? And so every object experiences this drag force. And there's no need to go through the derivation, but this drag force is typically given by the drag force that is exerted on a sphere of radius r that is falling with a velocity u in an atmosphere with density rho is given by this formula here. Again, it's interesting that there's a pi, but we don't need to go through this. Okay, so this is the formula. Rho here, I said it's the density of the air. If you were moving in water, it would be exactly the same thing. So it's the density of the fluid, just to be a bit more correct. The CD here is a coefficient that is known as the drag coefficient, and this typically depends on the fluid that we're talking about. Also, last lecture we had introduced the Reynolds number, and this Reynolds number depended on these known objects that we talked about here, but also depended on the viscosity of air. And so we can rewrite this drag force. We can rewrite it in terms of the Reynolds number. Nothing particularly profound going from here to here, just a simple rewriting. Okay. Excellent. Okay. The sphere is falling under the action of what I'm saying, of the gravitational force, which, again, I hope this is known to everybody. G, and G is directed downward. G, the modulus is 9.81. Typically, this varies from point to point on Earth, but that's what it typically is. We are assuming that that the sphere is, we're thinking about, when here, I'm trying to keep it generic by saying sphere, but I'm thinking about a raindrop falling through air, okay? And so normally you would write M, okay? But because we know that we're dealing with liquid water, M is also density times volume, and remind you that this sphere, so this is for third pi r cube times rho, okay? And so Fg is 4/3 pi r cube g rho L, because this is the density of the liquid. Why is there a minus rho? Anybody knows that? Well, this is the Archimedes buoyancy. Archimedes. Let me write it correctly. Archimedes. Okay, so you know the whole story that, he had been asked by the king to find a way to discover if a golden crown that the king had been given was indeed made of gold. And, the king said, find a way that doesn't involve deforming this crown. And, Archimedes one day was taking a bath, and he realized that a body immersed in a fluid moves an amount of fluid that's proportional to its mass. So he jumped out and shouted, "Eureka!" You know the whole story. Sorry, this was the worst way to recount an anecdote, but whatever. Okay, so at some point, so long story short, that's why there's the minus rho, okay? And there's a minus because this gravitational force is going down, but the Archimedes force is going the other way, okay? It's the buoyancy is directed in the other way. So on this raindrop, this raindrop is falling. We have two forces. We have gravity, okay? We have drag and drag. Sorry, we have gravity. We have buoyancy. Just to be consistent. And then we have drag, and drag will tend to slow you down. Okay. Equilibrium between these three is reached when these two forces, Fg and Fr, are equal. Okay. Typically, the buoyancy is a lot smaller than gravitational force for a raindrop. This is of the order of a kilogram per meter cube, and this is of the order of 1,000 kilogram per meter cube, right? So this is a lot bigger than this term here. And so typically, the main balance is between these two, drag and gravitational force. And you can do the calculation that when that happens, when the balance happens, the speed u squared depends on these variables, okay? And interestingly enough, it is directly proportional. The square of the speed is linearly proportional to the radius of the droplet here, okay? There's also, there are ways to manipulate this. Yeah, you can rewrite it in terms of the Reynolds number, and if you do, that's what comes out. Now, you may be slightly confused because now we went from a regime where we had u squared proportional to r, and now here I'm writing that r was proportional to r squared. Well, I mean, this is just because we are rewriting things, right? And so we're writing things in terms of the Reynolds number, which I remind everybody depends on u and r. Okay, so the dependency of nothing really changes. It's just that some dependency of u and r I pushed into the Reynolds number here. Okay. Okay. K1 is of the order of 10 to the 6 per centimeter per second. Okay, this is the constant here that I used to write this down. It turns out, I mean, because all these, well, okay, I'll say this later. Sorry. This law here that we derived is known as Stokes' law, and it applies to fairly small droplets of a radius that is as big as 30 micrometers. Okay, excellent. Now, interestingly, at very high Reynolds number or at high Reynolds number, we can CD is kind of constant, and we can rewrite the law that regulates the fall speed, the dependency of the fall speed on the radius of the droplet. And this is more similar to the law that we wrote before, and u now went like the square root of r. And this is typical. This is typically true for droplets that are fairly big. Now we're talking 0.6 millimeters to 2 millimeters. Okay. And finally, in intermediate ranges, it can be shown that u goes linearly with the radius. Okay, so we have u goes as the square for really small droplets, and then it goes as linear behavior for intermediate ranges, and then for really large droplets, u goes like square root of the radius. And this is important because terminal fall speed is kind of what is responsible. Well, is one of the main responsible factors for collisions to happen. Okay, this is giving you a quantitative way to determine the fall speed as the droplet grows. But what this is saying is that u is a function. The terminal fall speed is a function of the radius of the droplet. And if you have droplets of different radii, they will fall at a different speed. Okay, and so this is not guaranteed, but it's likely that they'll collide. If they're close enough, both in terms of their vertical distance, but also in terms of their horizontal distance, and we'll talk about that in a minute, they'll probably collide. Okay, so it's very important that u is a function of r, because otherwise they would all fall with the same speed, and the chances of them actually meeting each other, they'll be much, much smaller than they are in reality. So before we talked about coalescence efficiency, and we said, well, coalescence efficiency is the ratio, or you could also call it the chance, that two droplets stick together once they've collided. But what about their probability of colliding? So what about the collision efficiency? This measures essentially the chance, or it allows you to estimate the probability that two droplets, one of radius big R and one of radius small r, that are where one is overtaking the other. Okay, what is the probability that the two will collide? So this is small r and this is big R. This is falling at a greater speed. Okay, so it's overtaking the small one. What is the probability that the two will collide? Now, again, this is something we'll talk about in a minute, but you may think that this is obvious, that, oh, well, the probability is 1. I mean, provided that they're close enough, probability is 1. Well, it's a bit more complicated than that, but let me not ruin the surprise. Okay, so what you'd think is that the collision efficiency is pretty simple, right? And it can be computed simply as sort of something that depends on their horizontal distance, right? And this, again, we're assuming that these droplets are perfect spheres and kind of hard spheres, if you will, okay? And so, sorry, I'm just looking for, okay. So, the collision efficiency we define in this way as the ratio between two positive numbers. Okay, let me draw sort of what the collision will look like. This is the center of the droplet that we project down, and we may have a second droplet here. The center we project down. This has radius r, and this is radius small r. And the distance between the two is, we call this x, okay? Okay. Now, collision efficiency is defined as, for given values of small r and big R, this is x0 is let's say a critical value of the impact parameter that below which collisions are certain. Okay. So these can be essentially, this quantity can be related to the probability or to the fraction of droplets, if you will, of a given radius small r that this larger droplet will encounter while falling down. Okay. The collision efficiency is in a way related to the probability of collisions between these two. Okay. So the figure here shows you for the ratio, for a ratio of these two droplets. So instead of having a three-dimensional plot with small r, big R, and the collision efficiency, here it simply takes small r over big R. And it shows how collision efficiencies vary between different experiments. And in particular, each one of these curves refers to different values of big R. Okay? So I hope this is clear. What is the collision efficiency, meaning what is the probability of colliding? For droplets, small r and big R, the larger droplet, the different curves refer to radii, different radii of the larger droplet, and the x-axis is the ratio of the smaller radius to the larger radius. Okay, this gives us a way to compare all the different curves, because otherwise, if you just had small r here and the different curves, that would be all over the place. But in this case, the x-axis is bounded from 0 to 1, and there's a simple way to compute it. Notice that just like you would expect for really, really large droplets, for really large droplets, so for droplets of 50 micrometers, 30 micrometers, collision efficiencies very quickly saturate to 1. So when the smaller droplet is really, really small, then the collision efficiencies are kind of small. But it doesn't take much for collision efficiencies to go, to jump to 1. Now, you may be asking why is that? Why aren't these curves just horizontal? right? Why does it go down why do these curves go down like these? Well, you have to imagine what might happen when you have a really large droplet that's falling down and you have a smaller drop, right? If you're thinking about the analogy of like a bowling ball and a ping pong ball, and you're shooting the ping pong ball against it, the ping pong ball will hit this, no problem. But actually, in the air, when these are real droplets, as the larger one is falling, the flow, let me draw the flow will push against it and diverge, right? The flow of air around the droplet. Right? This is kind of intuitive. And behind here, that may be a turbulent wake. Okay? And so if you're a really, really small droplet, because you don't have a lot of inertia, if you're a small droplet, you may actually just end up following the flow as it goes around the droplet. So even though you are sort of within the range of a full collision, it might still happen that the collision doesn't happen. Okay. So the x0, meaning the value of the impact parameter, which is the distance between these two centers, the value of the impact parameter for which the collision is certain might actually be 0. Okay. Okay. So it's kind of interesting that these curves have actually a pretty complicated behavior. All right, they're not as simple as you might think. Yeah, just think what's being said here. Notice that so when you have when you reach a certain when you pass a certain ratio of the radii, okay, so for big R over small r equal to 0.6 or greater, so in this region here, well, here you have two different kinds of behavior. In one case, or you might have two different sort of counteracting effects, right? The first one is that now you have roughly, well, you started to have roughly similar droplets now, okay? And so they're different in their vertical velocity. Now it's starting to become smaller. And so while before, when you were thinking about this was like shooting a ping pong ball. Let's make this bigger. This was like shooting a ping pong ball. Now you're still shooting, you're still sending this against the other, but at a much, much lower speed. And the speed, the kinetic energy, if you will, that you give to one of the two droplets might not actually be enough to overcome the surface tension that acts as a potential barrier. And so this might actually get swept away. Okay. On the other hand, what might happen is that you could have, because you could have a bigger chance that one of the smaller droplet here is captured in the turbulent wake and hits the droplet here. So which one dominates kind of depends on many different effects. And it looks like when the larger droplet is really large, then it seems like collision will happen almost certainly. So you have this large droplet and a fairly large one, and this, they'll kind of, collide with each other. But I'm sorry, this drawing actually made no sense. But anyway, you have two really large droplets. Their surface tensions are smaller than if they were really, really small droplets. So it's kind of easier for them to collide, okay? And maybe the wake effect also helps in this case. That's what I wanted to say. But in this case, when you have really, really small droplets, maybe they don't actually collide because their terminal velocities are, again, very, very similar, but now surface tensions are pretty high for these two guys. And so maybe they will not collide. Maybe this will just be swept away by the falling one. I hope this was clear and I didn't just confuse you even more. Okay. Last couple of things, I wanted to derive a simple equation for growth of a droplet that is falling and that is collecting other droplets by collision. So let's suppose that we have a very simple system where a larger droplet of big radius r is falling at a given terminal speed that we call u of big R. And let's assume that around it there are a number of droplets, smaller droplets. Now, look, for the sake of argument, let me assume that these all have radius r and fall speed u of small r, okay? Now, we still believe in Galilean relativity for this, and so this falling at u of r and this falling at u of small r, it's the same as this one here falling at u of r minus u of r, and these guys not falling at all. Okay, this is a 0, right? It's the same thing, right? Because now we're assuming that we are in a reference frame. We're in the reference frame of these smaller droplets. So these are not falling with respect to us, and this is falling slightly lower. Okay, excellent. Now, how many smaller droplets is the large droplet going to encounter? Well, I mean, every second, this guy here is going to draw a cylinder, right? Well, yeah, whatever. Yeah, drawing is not my strong suit. How big is this cylinder? Well, this particular droplet will have a base that measure pi r squared, but that's not the cylinder that we're interested in because because the collision might happen even though the center of these droplets is outside of the cylinder. Do you see what I mean? So the cylinder that we're interested in is not necessarily what is swept by the larger droplet, but is slightly bigger because it also needs to take into account that the other droplets also have a finite extent, right? And so you might imagine this situation where you have this larger droplet that is colliding with a smaller droplet, and it's colliding just by this point here, just one single point, right? Now, this is big R, and this is small r. And so what matters here is not, is not big R, but it's the sum of these two, right? This is as far as this is the furthest that the two centers can be for a collision to happen, okay? If this guy was a point-like object, then yes, I would say, yeah, it's a cylinder. No need to worry about anything else. But because these guys do have a radius, it could be that only one single molecule of water of this smaller droplet touches another molecule, the other droplet, and it's good enough for us. And so we need to take into account a larger radius, okay? And so the base of the cylinder would be a little bit bigger, and it will be pi r plus r squared. And then this height, the height will be the velocity times the time that has passed, okay? We're counting the ratio of collisions, and so we're counting per units of time, and so we only need the velocity here. And the velocity of this guy is the difference between u of big R minus u of r, okay? It's kind of small to see, but it's what I wrote here, okay? Excellent. Now, Okay, so this is one thing. But then we also want to compute. I mean, in order for this to be applicable, we also need to know how many of these smaller droplets there actually are, right? If we want to know how many collisions there are going to be, how many droplets are we going to find inside of the cylinder? Well, this is exactly what's measured by the distribution function, right? So we have to multiply this thing by, I'm still not completely used to the to drawing with this pen and still make mistakes. N of R dr. Okay, this is the number of droplets, of small droplets of radius between R and R plus dr. Times, we also need to consider what we call the collection efficiency here. That is essentially the product of the collision efficiency and the coalescence efficiency. So remember, here we want to know how the larger droplet is going to grow. So first we need to measure how many collisions there are going to be, but then we also need to estimate, we'd also need to include in this calculation the probability that a collision is going to happen and the probability that a coalescence will happen in the end, will result from the collision, okay? So this E prime takes into account both collision and coalescence efficiency. We'll simplify our lives in a moment, okay? Okay, so this is brilliant. Now, we are collecting all the droplets that have a radius smaller than big R. Why is that? Well, this is kind of intuitive because R is falling faster than all these smaller droplets, right? And so it's going to overtake all of them. But larger droplets are actually falling faster than big R. They may indeed affect big R, and so this guy may be, included, may be the smaller droplet for some larger droplet. But for the sake of argument, let's just say that we don't care about this process, and we only care about what this guy here is going to collect while it falls in the atmosphere. So the only thing we need to do is take what we wrote before, exactly that, and integrate over the radius. We want to, in particular, we want to compute the rate of increase of the volume of the droplet, okay? Because we care about the increase in mass, and so the volume is the volume of the droplet is a better measure, if you will. And so for that, you'd only, it's a very simple modification. Just include the volume and make sure that this is, just include the volume here, and that's it essentially. Okay. This is the volume of the smaller droplet. Okay. And this is the volume of the larger droplet that is increasing. We're integrating over all the smaller radii. Okay, so we're just taking a simple integral. And this can be computed very simply. Now, big V is 4 over 3 pi r cubed, right? And so dV, I don't need to do this, but I'm sure this is obvious to all of you. It's 4 pi r squared dr over dt. And again, r is, for the sake of this integral here, r is a constant, right? So we can bring it in and move it around. So the 4 pi simplify with this, and we can bring an r square at the bottom of this, okay? Now, we don't need to get into the nitty-gritty, but essentially, essentially you can compute that. You can look at the book if you want the details. But if you solve all these, this integral with some kind of, with a few assumptions, and if you substitute, for example, E, you substitute it with E bar. You substitute it with some an effective average value for the collection efficiency, for example. Then this can be taken out of the integral and it simplifies. And we can also introduce M, this M here. Well, wrote it down. M as the mass of the cloud liquid water content per unit volume. Okay, and this essentially takes care of all these N of R and whatnot. And so this simplifies things tremendously. We can also say, well, U of R, we can say that U of small r, we can neglect that. And so we only need to take into account the velocity of the larger droplet. And essentially, with all these simplifications, we can get to this formula here. And this formula here, what this says, it gives an increase. It tells us how much the radius increases for a displacement, an infinitesimal displacement dz. Okay. Notice that it has a minus sign, so it doesn't quite make sense, right? Because rho of L, this is 1,000 kilograms per meter cube. This is certainly positive because it's a mass. This is a coefficient efficiency. This is an efficiency, so it's it's bound from 0 to 1, right? And so why is this a minus? Well, we're thinking about a droplet that is going down, and the droplet increases going down, right? But the vertical axis is pointed in the other direction. And so if you were to look at the radius going up, you'd see a radius that is actually shrinking, right? If you were to choose a vertical axis that is falling with the droplet, then dz would go in minus dz, and this would turn into a plus sign. But so that's why there's a minus. But this is important now because this formula now you can use to predict how much your droplet is going to grow because of these collisions. Okay, so we have something that tells you how the radius of a cloud droplet increases because of condensation, and this tells you how this increases as a result of collisions. That equation, if you remember, I'm not going to write it down, but it was r dr over dt, right? Equals something. So this is dr over dz. Can we have dr over dt? Of course we can. Dr, well, if you will, dr over dz, this is very heuristic, but is dr dt times dt over dz, right? Where this is the velocity of the droplet, okay? And so very simply just put in a droplet velocity, and this becomes dr over dt. Very simple. Okay, I think this concludes the things I wanted to say for now. So yeah, we started with a general problem of what's going to happen when you have droplets inside of a cloud. We saw that condensation cannot be the only process that's at play here because it wouldn't be strong enough to cause broadening of the spectra that we observe. And so it has to be something else. And we saw that it is coalescence, and we derived a very simple formula to predict how the radius of a droplet increases through collision and to coalescence. This is all I had to say. As usual, for any question, please let me know. Feel free to get in touch, email, phone, Skype, and whatnot, and I'll be happy to answer to all your questions. Thank you very much, and I'll see you again in the next lecture.